Now for this roller coaster, we can see that the car starts up at the top at 1, top of the first hill. It goes down to point 2, up over the hill at 3, around the loop from 4 to 5, and then it stops at 6. And we want to know, assuming no friction, how tall does that first hill have to be to get the car around the loop? How high does the first hill need to be for the car around the loop if there's no friction? So if there's no friction, then we know that energy is conserved from the state 1 to state 4. Looking at this, what types of energy would the system have at state 1? Well, up here, it just has potential energy because it doesn't start moving until it slides down the hill. So it gets going faster and faster and faster until suddenly at the bottom at state 2, it has all kinetic, zero potential. So then it goes over the hill and around the loop. So at 4, it's moving and it has a potential energy. So there's kinetic and there's potential because it's off the ground and it's moving. But for the car around the loop, so the very minimum height that the hill would need to be for the car to go around the loop is going to depend on how fast the coaster needs to be moving to make it through the loop. So if we start by drawing the free body diagram, up here at the top, then we have the weight pulling down, and we've got centripetal force pushing up, and then we've got the normal force from that track on the car pushing into it. So as the car is going faster and faster, it pushes harder and harder into the surface and the normal force will increase. If the car is going slower and slower, the normal force decreases until the car is going so slowly that it just falls. So at the point when normal force equals 0 is the minimum speed that the car needs to be going to round the loop. So first, we need to find minimum speed. And second, we can find that minimum height. So this is important. If normal force equals 0, then that is minimum speed around the loop. Because the faster the car is going, the harder it pushes into the track. So if the track is no longer pushing on the car, it's going to fall. So we can sum the forces in the y direction equals 0. So we have mv squared over r going up, minus mg going down, minus normal force going down, but normal force is going to be 0. So now we have mv squared over r equals mg. Masses cancel. V squared equals rg. Okay, so this is v squared, that's squared minimum speed to round the loop. So now we know what this speed is in terms of system parameters. So now to find h, we can use conservation of energy. So we know that since there's no friction and there's no pushing, no work is going to be done from 1 to 4. So all we have is energy. So potential energy at 1 plus kinetic energy at 1 plus work from 1 to 2 1 to 4 really equals potential energy at 4 plus kinetic energy at 4. And we said, well, there's no friction here, so there's no work. At state 1, it starts from rest at the very top of the hill, so there's no kinetic energy. And now at state 4, it's moving, so it's got kinetic, and it's above the ground, so it's got potential. So now we can go and put in the formulas. So we say this is the 0 point. We'll have m g h equals potential energy at 4, which is going to be m g times that height, which is twice the radius, 2r, plus 1/2 m v squared. But we know v squared is the same as rg. So we'll write that. Now conveniently, the m and the g cancel. So we cancel mg here, mg here, mg here. So that the height that hill needs to be does not depend on the mass of the car. So it doesn't matter how many people are riding the roller coaster. They can still make that hill the same height. Also, doesn't depend on what planet you are on. So now we know h equals 2r plus 1/2 r equals 2.5 r. So h has to be 2.5 r minimum for that car to go around the loop. And this is interesting. It can't just be double r, because you think, so double r would be the height of the top of the loop. But if the starting hill is only that high, then the car will not be moving once it gets to the top, and it won't go all the way around the loop. So that's why first we had to find that minimum speed to round the loop, and then we could find the minimum height. The textbook, this is a pretty interesting problem. So problem C14-1, they show this roller coaster. And the roller coaster, you can see it starts up at the top of this hill, it goes down here, it goes around the sort of sideways part, makes a loop, and then it goes back up, and then it does the whole thing backwards. This roller coaster is called the Raging Cajun. It's in the Dixie Landing theme park in Baton Rouge, Louisiana. So I rode this coaster a lot growing up. And one of the interesting things about it is that although in an ideal world, there is no friction on the track, in real life, there is friction. So even though they made this hill pretty high, a lot of times as the car was going around, it would get stuck on the sideways part because it wouldn't be going fast enough to make it over because it lost so much energy due to friction in the path from going down all the way through and then going around. So lots of people got stuck here, and you can even see right here how there's this ladder with stairs, like they ended up putting these stairs on there because people would get stuck on the sideways part and have to climb down. And so anyway, this coaster is still standing today, and you can go to Dixie Landing and ride it if you want and experience the dynamics of a roller coaster. So if you want to see the video, click the link. Trying to design a roller coaster, make sure that you make this hill more than 2.5 R, because in real life, there will be friction on that track.